Now, before we go on to looking at economic problems in the calculus of variations, particularly known as the optimal control theory, we want to look at some linear variational problems. Suppose we have a linear control problem where we have small u of t is an element of the set u of control variables, where we select u of t to be between some maximum control variable u of big M and above, so a minimum u of lowercase m. The state variable is xt, with x at time t0 equal to x0 and x at time 1 equal to x1. So then the problem becomes to maximize the path of the control variable between time t0 and t1, where we have some objective function f of t and x plus g of t of x multiplied by the control variable. And then we take the integral of that with respect to dt. And dx dt in this case is the partial of the function f with respect to t, and we denote that with that subscript 1 to indicate it's the first variable in, or the first parameter of f. And we do the same thing with g1, so it's the partial of g with respect to t, all multiplied by mu t. So assuming that g1t of x is not equal to 0, we can eliminate the ut from the objective functional, giving us the following result, that we want to maximize the choice of, or the path of x of t between t0 and t1 of big G t of x plus h t of x, x dot. Notice that previously in our discussions we had a y prime, because y prime was dy dx. Now we have x instead of y, and we have x dot, which is dx dt. And we integrate that over dt. And notice that we have these functions a xt and b xt. So these are the minimum that corresponds to the lowercase control u m, and b xt corresponds to the uppercase u big M. Okay, so this is the familiar calculations of various variations problem. And recall the Euler equation, which in this case is written as the partial of f with respect to x minus the derivative with respect to t of the partial of f with respect to x dot, and that's set equal to 0 as usual. Now, if we maximize this function f of t x dot, the integral, rather, of that function with respect to dt requires that f, the partial of f of x dot, the partial of that with respect to x dot, so in other words, the second derivative of the function of x with respect to x dot, has to equal 0. But this does not generally hold. And if we did solve the Euler equation, however, we would get this relationship here, that the partial of g with respect to x is equal to the partial of h with respect to t, and that would then determine our nice smooth x star t path. All right, so this would establish an implicit relationship between x and t, and any piecewise smooth function x star of t satisfying the above equation is a singular solution to the problem. The unique singular path, x star t, where t is between t0 and t1, will satisfy the x star at t0 equals x naught and x star at t1 equals x. And I'll have to put a 1 there by mere chance. So in other words, the solution that we find x star only includes these two transversality conditions by mere chance. So what do? If x naught is greater than x star at time period t0, then we want to reduce x as fast as possible to get to x star as fast as possible. And we would then set x dot equal to ax of t. If, on the other hand, the starting value of x naught is less than x star at t0, we have to increase x to get to x star t as fast as possible. So in that case, we would choose the higher of these, and we're going to show that in the diagram below. We want dx dt to equal to bx of nt. Now, if x1 does not equal x star t, so at the end period, if it's not equal to x star t, we use the same argument as in 1. So we get off the optimal path as quickly as possible, moving towards x1. And the same thing if xt is equal to x star t for this in-between period, then we follow the optimal path. So here what we have is a red line that is optimal, but the dark line is the path that we have to choose. So this is famous. This is Samuelson's famous turnpike theorem, of course. So if you think of this red line that comes through here as being the turnpike, and you're living off the turnpike, off the freeway, and you want to get to the freeway as fast as possible, and then take the freeway and then get off it to get to your destination. That's the same thing here. So if x naught is above the value of x star t at this point, you want to get down as quick as possible to the turnpike, to the optimal path, follow the optimal path, and then get off it at a particular time, tb, to get to your final destination. So think about that when you travel. All right, that's the turnpike theorem. Now, the other possibility that you have is that x naught is fairly high compared to where we want it to be. Then what happens is you try to go to the turnpike, you don't quite get there, and you go back following this line here, and you end up at x1. So this is a case where you really don't hit the red line, the optimal path. And this is known as the most rapid approach theorem, or as I mentioned, Samuelson's turnpike theorem. We also have the case of blocked intervals. So here we have an optimal function given by this black line and denoted by x star t, and we somehow prevent this area here. So you can't follow this across that area because there's a limit as to the value x could take. And in that case, whenever xt does not coincide with the singular path x star t, then one of the control constraints, u equals u lowercase m or u equals uppercase m, must be in effect. So here we have a blocked interval, and at tb, so we follow the optimal path to b, then we follow the path along to e, and then we head up and go through to g. So instead of going a, b, c, d, e, g, we end up going a, b, c, e to g, because we have a blocked interval that requires us to be at this value of x. So x follows a, b, e, g rather than a, b, c, d, e, g. Now consider the linear variational problem in the context of the maximum principle. Now, we haven't talked about the maximum principle yet, but we're going to discuss it in the next lecture. But then in the context of economics. So let's let j equal the integral from 0 to big T of this function here, where note that we have this x dot here, which is dx dt, and this is the integral over some time period dt from 0 to big T. We again constrain the value that x dot can take between a and b here, and we let x dot be equal to the u, the state equation where u is the control variable. So we write the Hamiltonian as the objective function this objective function with the x dot u put in place here, plus the what we know as the Lagrange multiplier times this constraint here, because this is the constraint on the state equation. And we'll get into more detail in later lectures. The optimal control, u of t, must maximize this expression. So we define sigma t as being h x of t plus lambda t, and that allows us to rewrite this function, this Hamiltonian, as g plus h plus u, where the h plus u is, the h plus lambda is all multiplied by u. So we have hxt plus lambda t, and that we define to be sigma t, and that ends up being multiplied by the control u. So now, if ut is equal to bxt, the solution is that ut is equal to bxt if sigma t is greater than 0. And if sigma t is less than 0, we set it equal to axt. So in other words, our controls are limited to these two. And what we're doing is, if sigma t is greater than 0, then we go to the highest level, and if of the control b, and if sigma t is less than 0, we choose the lower level. So we're getting a bang-bang control here. The control takes on these extreme values and is therefore called a bang-bang control. And sigma t is referred to as the switching function because it switches from the A to the B. Now what happens if to the control when sigma t equals 0? So when sigma t equals 0, the Hamiltonian is independent of u, so that the maximum principle does not specify the value of the optimal control. So the singular case is this: sigma t equals hxt plus lambda t equals 0. Now that's very familiar because it's very much the same as equation 1 above, where we argued that dh partial of h with respect to t is equal to the partial of g with respect to x, as giving the optimal path. So this gives the singular path where x equals x star t. So therefore, sigma t equals 0 corresponds to the singular solution x equals x star t. So the maximum principle now implies that the optimal control, u equals x dot, for the linear problem is a combination of bang-bang and singular controls. So we can see that best in this diagram, where we have an optimal x star occurring here. So that's what we'd want to follow, but because the initial value of x does not equal x star, but is x0, so we then follow this line here where h is at its maximum. Let's say that h refers to harvest. So we maximize harvest, so this is our b from up above, and this is our maximum harvest, and then we follow this path of x equal to x star where the harvest is at its optimal level, and then again we now drop, and this should be a minimum, not a maximum, and we end up, this is a maximum, and we end up going to xt. If it were the other direction, if we started here, we would then choose the minimum in order to get those endpoint conditions. So here we have bang-bang controls being applied in this region from here to here, and then again from here to here. So in the next lecture, we will look at the economics of this in more detail. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.